it is a section 3.23, polynomial interpolation. Let's see the theorem. Weierstrass approximation theorem. Suppose f is in CAB. This notation means the function is continuous over the interval AB. Then, for each epsilon positive, there exists a polynomial P such that the difference between F and P is less than epsilon for all x in the interval. You can choose epsilon arbitrarily small, but for the choice, again, you can find a polynomial such that this inequality is satisfied. The theorem implies that every continuous function can be approximated by a polynomial arbitrarily close. Let's see another theorem, polynomial interpolation theorem. x0 to xn are n plus 1 distinct real numbers. Then, for arbitrary values, y0 to yn, there is a unique polynomial Pn of degree at the most n such that Pn at xi is yi for all i's. In this case, the graph of y equal Pnx will pass all the points xi, yi. An implication of the theorem is that for values at n plus 1 distinct points, the interpolating polynomial Pn of degree at the most n is unique. So once you construct a polynomial, interpolating polynomial, then even though you use you construct by using other method, various methods, the resulting polynomial must be the same. Okay, here, find the interpolating polynomial P2 passing the 3 points. Okay, let's see the data points. We'll try to visualize the data points. Okay, there is x and y coordinates. Here, x is minus 2 and y equals 3, so that we have a point here. And x is 0, then y is minus 1. There is a minus 1. And x is 1, y equals 0. So that x is 1, now y equals 0. So the P2 is a parabola, and parabola is passing these points, so that the shape of a parabola must be given in this way. Okay? If we try to find the polynomial, then we may start with y equal ax squared plus bx plus c. Okay. x is 0, y equal minus 1 means then 0 and minus 1. So that means c is minus 1. Okay, from here, ax squared plus bx minus 1, right? Now, we can decide a and b by using to the other points, other 2 points. Okay. Now, x is minus 2, then y equal 3, and minus 2 means that there's 4a, and minus 2b, and minus 1, and x is, what is that? X is 1, then y equal 0. So x is 1, y equals 0, so that 0 is x equal 1, a plus b minus 1. So from these 2 equations, we can get, okay, let's simplify. That's moving this other side, then it'll be 4 divided by 2. So that there's 2a minus b equal 2. For that one, a plus b equal 1. From here, we can get immediately, okay, a is 1, b is 0. Okay, a is 1 and b is 0. Okay. So here, a is 0, b is 0, c is minus 1. So here, p2 of x is now a is 1, x squared, b is 0, so there is no linear term, and minus 1. Okay, that's the final answer. Now, among many other forms, we'll study Lagrange form of interpolating polynomials. It is most popular one. Okay. Assume we have we are given data points xk, yk, and k is from 0 to n. So there are n plus 1 points, and these xi are distinct. Then the interpolating polynomial will be sought in the form here. Now, these are y values, y0, y1 up to yn, and then is y0 is multiplied with ln0, and y1 with ln1, and so on. Here, yn is with ln. So this is the sigma notation. We'll try to find interpolating polynomial in this form. Here, ln k, k is from 1 to n, 0 to n, are basis polynomials. And they can be made by using the nodal points x0 to xn. We'll try to construct them here below. Now, in this way, we try to get interpolating polynomial. For example, for 3 points here, and okay, case from 0 to 2, the Lagrange form of interpolating polynomial is given in this way. Here n is 2, and from 0 to here 2, and y0, y1, y2. In this way, we'll try to construct the interpolating polynomial. Now here, so then major thing is, now we have to know how to construct the basis polynomial ln k. Now, to get idea, we start with a very special case. And all the ordinates be 0 except for 1 occupying the ith position, which means that yi is 1 and other ordinates are all 0. Then, once we start with this special case, then Pn of x given in this summation linear combination can be written in this way, ln I. yi is 1 and every other y values are 0, so that we have only one term. Once here xj is used to, then we have here Pn xj is ln I xj. And on the other hand, for this data, and Pn, once we construct polynomial, then, and to satisfy this condition, the theta, it should satisfy this one. Pn at xj must be delta ij. Delta ij is the Kronecker delta. If ij are the same, then the value is 1, and different, then it's 0. So only here, that one is now at xj, the value is 1, but for all other points, the value must be 0. Now, we combine them here to reach this identity, and ln I xj must be delta ij. And such polynomials are called cardinal functions. Okay, so let's see example. When n equal 2, okay, let's see n equal 2, then here there are 3 points. There is x0, and now x1 and x2. Now L20 is now only 1 at x0, so that here the value is 1, and at other points the value must be 0, which means that the shape is given in this way. There is a quadratic, and there is L20. Now L21 is at x1 the value is 1, and at other point the value is 0, so that it is going like that. So that there's L21, and L22 is 0, 0, 1, so that, yeah, that way. So that is L22. In this way, we will try to get the cardinal functions, the basis functions. Okay. Now, we'll see here how to construct such cardinal functions. Now, we'll focus on Ln0. There are n plus 1 point, distinct points, and for the first point x0, we'll try to construct the cardinal function. It must be 1 at x0, but at other points, the value must be 0. So here, from x1 to xn, the value must be 0, which means that for each of these points, this function should have a factor, x minus x1 and x minus x2, and so on, so that here the Ln0 should have this factor, so that at x1, x2, up to xn, the value will become 0. Now, this one is already nth of the polynomial. So possible changes only along with the constant multiple. So we start with that one for Ln0. Now, this one should satisfy the other one. The value must be 1 at x0. So we put x is x0. Then the value is 1. Now here x is replaced with x0. We have that. But we start with the distinct x values, so that this product cannot be 0. So that we can solve the equation for C, and we have here. We combine this one and that one to reach at this final form. This is just with product notation is made. Now, you can see a pattern here. It cannot have x minus x0 factor, because at x0, the value must be 1. But for other points, the value must be 0, so that we have this factor. And then we copy them to the bottom, and x is replaced by x0. So that's it. Now for other points, so ln I, so it is now point xi. So we make a product, but it cannot have x minus xi. So j is moving from 0 to n, the product, but j cannot be I. And we have x minus xj, and copy it to the bottom, and x is replaced by xi. So in product form, it is given in this way. Okay, let's try to solve some problems, examples. Okay, now determine the Lagrange interpolating polynomial that pass it through 2, 4, and 5, 1. For this data, you may get a table, for example, xy, and then x is 2 and 5. For 2, y values 4, and for 5, y values 1. Okay, once you make this table, then it's quite clear to see data. Okay. Now here we have to get the Lagrange cardinal functions, but before constructing it, we may consider here the shape of the cardinal functions. There's 2, there's x0 and 5 and x1. Now this is linear, so that 1 here and 0 go down, and 0 here and 1 over there. That is L1, 0 is for x0. Now there's L1, 1 is for x1. Practically, L1, 0 can be gotten in this way. Jump x minus x0, and then the next one is x minus x1, and over now x0 minus x1. There's no other. So that's it. Now we are using the practical values. x1 is 2. So here's x minus 2. And now x1, okay, x0 is 2. And oops, x1 is 5. Right? And then 2 minus 5. So it is minus 1/3 and x minus 5. Right? Okay, L11 for this one. Now x minus x0 over now x1 minus x0, and we have to jump x minus x1, nothing else. So that's it. Here x0 is 2, x minus 2, x1 is 5. Okay, so that is 1/3 and x minus 2. Okay, so here the P1, the final interpolating polynomial, is now y value 4 times this one. That is a minus 1/3. Okay, third. Now x minus 5. And plus 1 times here 1/3 x minus 2. Okay, that's the final answer. You may simplify the result, but anyway, this is the final answer. Okay, let's try to do one more here. Now x0, x1, x2 are given, and use the points to find the second Lagrange interpolating polynomial P2 for fx is 1 over x. That means that we have to find the P2 on interpolating polynomial satisfying x values and y values gotten from this function. Okay, so let's try to make a table, data table. Okay, here 2, 4, 5. And then y value must be 1 over 2, 1 over 4, and 1 over 5. By using these 3 points, x0, x1, x2, we can get the P2. Okay, so it's a cardinal functions must be second order, and L2 for x0 is now. So we jump x0. Now x minus x1, which is 4, and x minus x2. Okay, divided by, we copy them to the bottom, the denominator, and then x must be replaced by here x0. So that is now 2 minus 4, and that is 2 minus 5. Okay, that is L20. And L21, you can get this cardinal function quite similarly. Now x minus x0, which is x minus 2, and x minus x1 must be jumped, and x minus x2, x minus 5. And copy these factors to the bottom and replace x with x1, which is 4. So that there is 4 minus 2 and 4 minus 5. And the same way, exactly the same way, you can get L2. You can finish it yourself. After getting these cardinal functions, now the P2 of x must be here, that y value, first one, y0, half times that one, L2, 0, plus now 1/4 times here, now L21, and plus finally 1/5 L22. Right? For example, that one on the bottom we have -3, -2, -3, so that and that is 1/6, and okay, these factors x minus 4 and x minus 5. And along with this half, it has 1/12 and these two factors. So for the others, you can check it quite easily. Just try to finish the computation yourself. Now, for that Lagrange interpolating polynomial, we may use a computer program, and you can use MathLab. However, MathLab is originally developed for the vector and metric simulation. You can do some symbolic computation, but it's not so much flexible yet. So you may try to use Python, and by using the symbolic package SymPy. And here we define Lagrange, that is x values, y values, the theta values. Once the length of them are different, then it's error and the program stops. Okay. Now we try to get the polynomial, start with 0, and we add them. And here, this inner loop, okay, that one, from here to there, that one is, okay, for each term, here we start with, for each term like this one, we start with 1, t is 1. Now, and j is moving the whole data point, and once j is not k, so this is now k is 0 here, not k, then for 1, we are multiplying x minus xj divided by here xk minus xj. That is multiplied. So it is making that 1. That is exactly following that formula right now. So we try to make here kth. We are using notation k, but anyway, kth that cardinal function here, and after making that saved in t, and we multiply y value and add to the polynomial. So a case moving from beginning to end. So that after that we return. Now here this is theta values, x values, y values, and we call the function Lagrange, and P2 has the result, and we print out P2, and after a simplification, again print out. Then results are given here. This is just a raw output, and this is simplified output. Okay, here this is yet a kind of a limitation. Rather than here some integer printout, right now we have some ratios. Okay, from here 1/3. If we try to express this portion by small integer, then 1/3 will come out, and 1/2 will come out, and there is a 1/2. So that half, 1/3, half, so that total is 1/12. So that is exactly that one. So it is the correct result. And after simplification, you have that. Okay? By using software, you can get interpolating polynomial quite easily. Once implemented, then you can use it again, right? Okay, we'll continue in the second part. Thank you.